Okay, so let's start with this session, afternoon session, please. Our next speaker is Juan Carlos Arteaga about the WHISP working group. Yes, thank you. The boss. Okay, thank you. So the next session is Juan Carlos Arteaga about the WHISP working group. So please go ahead, Juan Carlos. Thank you.
Thank you very much for the presentation. And all I want to thank all the organizers for the opportunity to give this update about the combined analysis of the WHISP working. So this is going to be the content of this presentation. It's going to be business introduction. Then I will pass with the experimental condition. Yes. Okay. Okay. So I will present a proof report on the combined analysis of the WHISP working group. Basically, what we have done is to study the data from different experiments. And the idea is to study the anomalies, some anomalies that have been discovered regarding, for example, the muon excess in, for example, experiment like the Pierre Auger Observatory. So this is going to be the content of this presentation. So first, very brief introduction, then I will pass with experimental conditions, then I will talk a little bit about the muon phase space that we are studying here, then we will go to the combined analysis, and by the end, a brief summary. So the motivation behind this analysis is basically to study the discrepancies that have been observed in the muon densities in comparison with the predictions of the high energy hadronic interaction models. That happens mainly between 100 PBs approximately up to 10 EeV, where these differences have been observed. So as a first step in order to try to understand these anomalies, the working group on the hadronic interactions and shower physics has made a first compilation of all of the available of several experiments about the muon density measurements in this energy range. This information comes from these experiments from 10 to 11 experiments like the Moscow extension shower array, Ice Cube, Cascade Grande, Nebot-Neckar, Pierre Auger Observatory, Sugar, the Telescope Array, and the Yakutsk Array. So all of this compilation was put together in the same framework. We have taken into account difference, for example, in the energy scale. So in order to try to make a comparison on equal in the equal framework. So this is a combined first combined analysis, a meta-analysis of this data. And we have used a common parameter for the comparisons, that is the Z-scale, which has already been presented before. And as I said just a second before, we have taken into account the difference in the primary energy scale among the different instruments. So what is the difference with the other analysis that we have performed? So basically, it is the same analysis that we have from the last ICRC 2023, but in comparison with previous works, so we have updated the result from the Yakutsk and also the Sugar experiments. We have also included data from the Havera Park from one analysis that was also presented at the last ICRC. We have also taken into account the estimation from the Cascade Grande data using as a reference scale the one from the Pierre Auger Observatory. And we have also started to review the detector characteristics and also the properties of the collected data. So this is the data that we have employed for this compilation. So the data come from different experiments around the world. We have, for example, here the data from the Pierre Auger, the high-res MIA, Telescope Array, Havera Park, Cascade Grande, iStop, also the Moscow Array experiment, Yakutsk, Nebot-Neckar. Here we have Agasa and also Sugar. Note over here that there are some labels in light blue with some dates. That is because this experiment are not taking any more data, but the experiments label in white, they are still working and providing information. So Here you can see in this table the different experimental conditions over which all this data was collected. For example, in the first column, you can see the name of the experiment, and on the second column, the kind of the detection technique that it was used in order to collect the data. In the case of the IceCube iStop experiment, we have data from the ice Cherenkov stations. Regarding the telescope array, they use the plastic scintillator array, and the Pierogi Observatory collected data by using the surface water Cherenkov array and also the underground scintillator modules. Regarding also the detectors that use buried muon instruments, we have, for example, high-res MIA with underground also scintillator counters, the Moscow array with the Geiger-Müller counters, the sugar experiment with the underground liquid scintillator tanks. We have also Yakuts over here with scintillation detectors. And on the other hand, we have also some other techniques which involve shielded detectors that involve scintillators. For example, like those ones used by the Havera Park experiment, the Agasa array, and also itself in the Cascade Grande detector. Finally, the Nebot Decor instrument used the detector and a water Cherenkov calorimeter. So all this data come from different experiments located at different vertical atmospheric depths. So you can see on the right-hand side an axis where you can see the vertical atmospheric depth of each of these instruments. We have that they cover the range from 690 grams over square centimeter at a high altitude, like in the case of iStop IceCube, up to almost the sea level, as you can see, for example, here, Cascade Grande. Here you can see Pieroget telescope array around some 900 grams over square centimeter. And in the middle, you have other experiments like Agasa, Moscow detector, Nebot Decor. And here, very close to the sea level, you have also Havera Park. You find sugar and also the Yakuts experiments. So that is important if you want to make a comparison of all of these different data. So now here you can see the different experimental conditions over which all this data was taken, and also how the analysis was performed. So here, for example, on the first column, you see the name of the detector. On the second column, you see the way in which the primary energy was estimated within each of these experiments. For example, it was estimated in an independent way, like by using the fluorescence detector technique, so which is labeled here with the FD letters. So you can find the high-res MIA, you can find also the Pierogi Observatory, you can find here also the telescope array. If it was used, for example, the surface detector in order to make the calibration of the primary energy, so we have added the label ST corresponding to surface detector. And here we have several of them. For example, the Moscow array, you can find also here the Havera Park detector, iStop, the Yakuts array, and also Agasa. On the other hand, there are also some methods in which there is an intercorrelation between the FD measurements and also the surface detector measurements, like the case in the Pierogi Observatory. So we can also add it here this information. And finally, we also added some last label in order to indicate those experiments which use an spectrum or reference in order to make the calibration of the primary energy. That is, they compare basically their energy spectrum with one of reference in order to make this cross calibration. There are 3 experiments. One of them is the Nebot Decor. Then we have sugar, and here in the morning presented also the results about the Cascade Grande detector, which you can see also over here. We explain a little bit about that. So on the third column, you can see here what is the muon contribution to the energy estimator. So according to each experiment, there are different variations. In the case, for example, of the fluorescence detector, seems to be smaller, like because that is a calorimeter detector more sensitive to the electromagnetic component. But as you can see, there is also some other experiments in which this, for example, on the ST, in which this muon contribution could be a little bit larger, as you can see over here. On the other hand, you have another column in which you can see if the analysis that they have performed was done by taking into account the full simulation of the detector and also of the corresponding simulation of the development of the air shower in the atmosphere. So, for example, all these experiments that have both of them have this small level, and the crosses indicate that they don't have the complete simulation or of the detector itself, or of the development in the completely reconstruction in the of the air shower with the techniques of the detector. So, for example, that happens in the case of sugar. We find also that the same case for the Nebo-Decor experiment, and also for the case of the Havera part. Also, here we have another experiment, which is Agasa. So the other ones satisfy all these conditions about the reconstruction and also the simulation of all the details of the interaction with the detector. And finally, here in the last column, you can see the vertical atmospheric depth that we presented in the previous slide. They cover a large range of atmospheric depths, which go from 690 up to almost the sea level, like in the case of the Cascade Grande detector. So all these measurements that we have in this compilation have different, cover different region of the muon phase space. We are talking about, for example, differences in the primary energy, in the energy threshold. We have difference, for example, in the radial distance to the shower core, the position in the lateral distribution, also, for example, the zenith angle, among other differences. So just to give you an idea of the difference between all these data sets, I will show you here in this and the next slide some plots in which you will see the differences, for example, in the muon energy threshold, here on the left-hand side as a function of the primary energy for the different experiments. That is the muon energy threshold at the ground level, at the observation level. So you can see here that the measurements cover from some hundreds of GBs up to some tens of GBs approximately. So on the other hand, on the right-hand side, so we have taken into account a correction by the energy loss in the atmosphere to calculate the energy threshold, both at the production site. And you can see here the plot as a function of the atmospheric depth. So there are several data points. So here, for example, you have some large variation in this energy threshold that goes from some few GBs up to some tens of GBs approximately. So you can see that there are some points which are joined by some continuous line. That is because we have taken into account here the differences because they are observing data from different zenith angles. If you use that from different zenith angles, so you will have a different energy threshold at the production site. So that is taken into account. In the case, for example, of the Cascade, you have also here in the case, for example, from the Moscow air shower experiment, etc. So on the other hand, here in this table, you can see the differences in the arrival direction of the data, which was collected by the different experiments as a function of the primary energy of the air shower. So the data points indicate just measurements on a limited region of the phase space. And here you can see also some bands which take into account that the data was integrated in all this region of the phase space. So for example, here in the case of Cascade Grande, there are data which was taken between 0 up to 40 degrees. Sugar here from 0 up to very inclined events. In the case of the OHA, for example, here you have events coming from the inclined directions and also almost from vertical directions over here, so etc. On the right-hand side, you can see here another plot where you can observe the radial distances at which all this data was measured. So cover from some measurements from very close to the shower core up to distances which go up to almost 1 kilometer, as in the case of the Nebo-Decor. All of this as a function of the primary energy. So these are mainly the main differences between all these data that we have collected in this combined analysis. So now, in order to perform this meta-analysis, we need a common parameter in order to make this comparison. This parameter is the z-scale, which is defined over here, like the differences in the logarithm scale of the mean number of muons. So the difference with regard with the predictions of the protons from the Monte Carlo models in comparison with the expected difference for the case of the Monte Carlo simulations for iron and also for protons. This parameter is defined in such a way that is the experimental number of muons is like the one predicted by the iron. So you will get that that value is equal to 1. But if it almost equal to the predictions of the protons, so you will have that this parameter is equal to 0. So this is the mean measure value, and these are the corresponding Monte Carlo predictions. So okay, by using this set scale, so we can make this comparison, and in principle, we can this definition eliminates the energy dependence of the data, and also it cancels also some possible linear biases. Or in addition, it can be also used in order to make comparison between the results of different experiments. Now, with here you can see a compilation of the different experiments that have measured data between 10 to the 15 up to a little bit above 10 to 18 electron volts. So you can see data coming from the 11 experiments over here. So OJ here with these data points over here, black red data points, and each panel represents the comparisons of this set scale as a function of the primary energy for a different high energy hadronic interaction model. So we have not only post-LHC hadronic interaction models, but also some pre-LHC hadronic interaction models, like the case of Civil 2.1 here. You have also QGet 203 and QGet 01. And the other ones were calibrated with the LHC. For example, here you have EPOS LHC, QGet 204, and some models for Civil 2.3 and different versions. The original model, and the version C. So you have also data from the telescope array. You have from IceCube over here, Cascade, Yakutsk here, Agasa, Sugar, and also here you have the Nebo Decor experiment. So you have over here the Javera Park, which is light blue, etc. Now, this comparison, in order to proceed with the analysis, must take into account the differences in the energy scale of the experiment. So in order to do that, so we need to adopt a common energy scale. If you don't do that, so you will introduce an offset in the number of muons and then in you see a scale parameter. So that is because of the dependence of the number of muons with the primary energy of at which you are making the study. So in order to take that into account, here, for example, you can see that differences of 20% offset in the energy scale can give you a difference of 18% shift in the muon content. So what the WHISP group has done is basically to adopt an energy scale by using the energy spectrum between the that from the Pierre Auger Observatory and also the telescope array. Please note that these spectra are the spectra from the telescope array from previously from 2019 and also the last one from 2020. I have seen in the last presentation that now the differences are a little bit smaller, so that must also be taken into account. But for the moment, we have taken into account the spectrum in the middle between these both of them, which were measurements that were taken with an independent primary energy calibration method independent of the Monte Carlo simulations. So by using this energy scale, so we have applied to independently to each experiment a correction, a shift in the energy factor in order to match each experiment with the corresponding energy scale of this spectrum of reference. So here you can see the different scales that we have applied in order to take into account these differences in the energy scales of the different experiments. So here, for example, the OJ has an energy scale of 0.95 approximately, because it is about the one which we are taking as a reference. The telescope array, which is over here, it's a little bit higher because it's the normalization is above of that of the energy scale, and so on. There are some experiments in which there is some misinformation about the methods of the energy calibration. So that's why we were not able to put here to find the corresponding factors in order to make the cross calibration. So basically, these experiments were not taken into account in the meta-analysis. So after correcting the different spectra and taking into account the differences in the energy scale, so we have found the results. So this is the scale already corrected as a function of the primary energy. So here we can see that there are at least up to 10 to the 17 electron volts. It seems that all the data seems to be in agreement with the predictions of Monte Carlo for pure protons, also for pure iron nuclei. But we see that above 10 to the 17 electron volts, there start to be some differences. So for example, very close to 10 to the 18 electron volts, it seems that this data seems to appear muon excess in the case of experiment, like here, for example, like the case of the Pierre of the Observatory, Nebo-Decker, and also the Havera Park detector. In comparison with the EPOS-LAC, we can also observe it here with QJ204, here, for example, with Civil, and Civil 2.1, and also here in the case of the telescope array. So, but there is also another set of experiments which doesn't seem to take this muon excess in the corresponding data. So we can see the cases from Havera Park and also Yakutsk, which seems to be in agreement with the predictions of the Monte Carlo models. For example, QJ01, EPOS, QJ204, and the new version of Civil. And there is a one experiment which seems to be for which the simulations seem, which is Cascade, but calibrated with the energy scale of the Pierre Observatory, in which seems to be the Monte Carlo simulations overestimating the corresponding measurements from the data. Now we can remove also the mass dependence of the C scale to see what is the behavior of the data. So here we have subtracted the corresponding value of the seed value from the GSF predictions in order to remove this mass dependence. And we have found these plots over here. Here on the left-hand side, we can see this correction, already corrected C scale as a function of the primary energy for the case of QJ04, and here for the case of EPOS-LAC. Here you can see the predictions for each of these models with 0. So what can we see over here? So we can see that it seems that this anomaly, this muon excess, seems to be energy dependent. At least what we see for the case of Nebo-Decker, also the Joyer experiment, Agasa, and Sugar. But we can also see that there are, again, a set of experiments in which there is a better agreement with the Monte Carlo simulations. So in order to see what is happening over here, so we need to take into account what are we measuring with the different experiments, what region of the phase space, if there are also some systematics, etc. So all of this information, it's very important. Finally, as a first step in that direction, what we have done is to make a comparison, for example, of the data with by classifying all these measurements according to the muon contamination in the estimated primary energy. For example, here you can see the data in which the muon contamination is basically close to 0. For example, because they are based on the fluorescent detector technique. OJ, you can see here ice cube, etc. It seems that there seems to be a pattern over here in which you can see that there in these measurements above 10 to the 17 electron volts, we can see the muon anomaly. I mean the muon excess in the data for all these kind of detectors. But as long as we go directly to other measurements, for example, the detectors that were calibrated by using a comparison with the energy spectrum of reference, so we can see different behavior above 10 to the 17 electron volts. Here, for example, you can see that in the case of the Sugar detector and also the Nebo-Decker, you can see the anomaly. But here, for example, you cannot see with Cascade Grande data calibrated with the Pierre Observatory. You cannot see that kind of behavior. If we go, for example, to those experiments in which the muon contamination is higher for the case of the calibration of the primary energy, so we can see, first of all, here in this regime, a good agreement, but at the highest energy, we see to be, the data seems to reveal again a muon excess in the data. So it seems that there isn't we should try to study more what is happening with all the differences in the muon phases, in the muon phase space, in order to try to understand what is happening over here. So this is the compilation of all the data by taking into account the differences in the contamination of the muon number. As you can see, there is not a clear pattern in the data. So in order to finish, so in this progress report, we have presented the WHISP update of the meta-analysis of different shower muon measurements. So in the range from 10 to the 15 up to 10 to the 19 electron volts. So in the ultra-high energy regime, we have found that, for example, Pierre Auger Observatory, the telescope array, Sugar, Agasa, and Nebot Decor show an excess in the muon number in the data with in comparison with the Monte Carlo predictions. So, but we see also another group of detectors in which this discrepancy is not observed. For example, Yakutsk, Javier Park, and also the Cascade Grande, calibrated with the Auger energy scale. As I said before, just to finish, to understand these differences, we need more to understand a little bit more the experimental conditions, how it related with the muon phase space, and the differences in the simulation characteristics. So that's all. Thank you very much.
Okay, perfect. Thank you, Juan Carlos, for this interesting talk. So time for questions. Yes. And then you, Carl.
Yeah, I have a question and a comment that are related. Could you go to slide 16?
Here.
Yeah, we have the ice cube and the Auger results here. And my question is about the energy scale. The choice of putting it between Auger and TA makes it so that the ice cube results are shifted by 20%.
Yes.
And the Auger results by 5%. If you would use the GSF energy scale on the other hand, ice cube would be shifted by 8% and Auger by 12%, I believe. So my question is, why was not the GSF energy scale used, which is anchored to direct measurements? And my comment related to that is that if you would use that one, the excess or the deficit in the Auger data would look a lot less crazy here.
Okay, the first question. The first one is because remember that Auger and also telescope array are using independent energy scales, independent from the Monte Carlo simulations. So the idea was to use some spectra which are in which this influence, this independence of Monte Carlo simulation is lower. So that's why. That is the first reason. So the second question, what was, excuse me?
Yeah, no, the second was just a comment that if you would use the GSF energy scale here, I think everything would shift down, and I don't think you would see the Auger points going beyond the iron line anymore. Or at least it would be.
I don't know exactly if that will happen when you use the ESF, when you use this energy scale, but it could happen. I don't know, so I cannot answer that one.
Yeah, actually, it's a comment. Yep, the comment to your question, Steph. It's that, in fact, so what Juan Carlos said is correct, but there was another reason which was historical, because this group was created during the UHECR conference, which is a working group between Auger and TA. So the choice was to use it there and not anchor to use the original GSF energy scale. That's the only reason. So each scale everything up down, as you said. But I mean, the message here is that the slope was, I mean, the first version at least, the slope was non-zero, and this was independent of the scale. So indeed, the scale can be shifted up down depending on your spectra choice. Yeah. But so there is no deep reason why. Yeah.
Okay, Juan Carlos, I think so. You still talk about the muon excess or discrepancy, but if the data you show is, to me, inconclusive. So maybe historically people thought that when they started, it's very obvious, but what you have as a compilation, it's at least not obvious to me. Yeah, it's and it's so sometimes one gets the impression you want to see an excess, but it's not. There are too many contradicting things in those plots, and well, so there are two things. Well, actually, several points I want to make. One is if we anchor to whatever energy scale, be it a direct one like AMS, going all the way to the highest energies, I don't think we are better than 20 or 30% because we connect many spectra. We lose the predictive power on the way because we have to connect measurements that aren't really going from the low energy end to the high energy end with this accuracy. There's no way, just with scaling. So I think whatever we choose there, we are not going to be accurate enough whether we go from the high energy end down or the low energy up. The other part is, and I'm happy to show it tomorrow in the discussion session, if one, so telescope array as well as Auger has done simulations to compare the ground signal with just the spectrum. And you can do it with iron, you can do it with protons and whatever. It really actually looks really agreeing very well with what you see in the detectors. So you do need a second independent measurement, otherwise you don't have the sensitivity. So in my view, actually, it's very, very hard, what you call flux normalized or whatever. It's excessively hard to get a solid prediction from those. Simply because we know when we started with those big experiments, it looked like everything is in agreement with the Monte Carlo. And only if you have like a really independent measurement, you suddenly see things are more complicated. I'm not saying that we are right with an excess. Yeah? So that's a different story, but you need an independent measurement. And I think that's one of the key reasons why those plots are populated with lots of points and we don't learn enough. Yeah. So for example, if somebody analyzes Agasa data, it's very hard. Or if you go to sugar data even, it's even harder. I don't know whether we learn so much from it. So we have at some point, we have to sort of clean this up. Yeah.
Yes, exactly.
And so you can use it as legacy plots but we have to, yeah. So we have to reduce the number of points. Yeah.
Yes. One thing that we can mention here over here, the first thing is regarding the linear spectrum. We must go from very well-known facts. As for example, the linear spectrum is the same for everybody. Using this fact, so we can make a comparison, and this is the result. So that must be the same for everyone.
No, but let's say telescope array can simulate, for example, the ground signal perfectly well with protons, even though they don't see only protons in fluorescence. But you don't see it in the distributions. And John can confirm that. It's just because of the energy spectrum, it's forgiving. You just don't see it. And same is true, by the way, with Auger. We have those plots. So it's very hard, really, believe me.
Yes.
Even if you do the analysis, you see it, but it's, yeah.
Yes, but also take into account that even in the same experiments, we can see, for example, Cascade Grande, Ice Cube, using the same ideas, you can see inside the same data, the several differences, using the same hypothesis. So if there were no problems with the muons, so everything should be in agreement, at least in one experiment. And it happens that we don't see even that. So there must be something over here.
Oh yeah.
And this is just a compilation, just to show what we have at the moment. But as I said before, we still need clean the data, filter, how it related with the different properties of the muon phase space. And I agree that is very difficult. So we need to see what we are measuring. If we can compare what can be compared and under which circumstances in order to make this kind of analysis. At the moment, this is just the situation. So as you said before, it could be that there is something there, it could be that not. But what we see is that even in the same experiments, even with the same hypothesis, something is happening.
Sure, but it is displaying that our models are not good enough, the hadronic interaction models, and maybe some of the measurements are incorrect. That's a different story. Yeah, but I'm not claiming that. Yeah.
So that is part of the work. Thank you, Ralph.
Okay, so a quick.
It's okay. Okay. So I have a different point. So now we have about the lower energy region. So we have the Lasso, the Tibet, and Alpaca. So do you think that also these lower energy regions should be also check the muon excess, muon numbers, or?
Lasso has shown from some talks that they have presented that there is an agreement with their data. For example, even the evolution with the zenith angle is also like the one that they have predicted with Monte Carlo simulations, up to energies of 10 to the 16 electron volts. So the measurement seems to be, at least up to now, in agreement. So they have not seen any difference, at least at lower energies.
But anyway, I think it's better to put the one point in this plot so that is a quite good indication. It's really that problem is happening only the high energy regions. That is just a suggestion.
Okay.
Yeah.
Okay, one question online. Please,
Yes,
can
actually, yes, thank you. Actually, it's just a comment. There is no access, and actually, the models at PV energies have a notable agreement with regards to the number of muons, but there are some discrepancies, particularly in the LDFs when you look. This has been published before, so we know that the models it will be very interesting in the future by experiments like LASSO or at the future SWGO experiment to have these measurements conducted, because we know that the data and models will not agree because models don't agree right now. But it's true that they agree in the total normalization of the number of muons.
Okay, well, thank you for the comments. Okay, let's thank Juan Carlos Sangay. Thank you for the talk.